Okay, so today we are going to discuss about differential inequality, and also we'll before going to differential inequality we'll also study the famous inequality that will be turn out to be very helpful and useful tool in our future analysis, that is Bellman Gronwall inequality. What Bellman-Gronwall state that if we have a positive constant c greater than is equal to 0 and we have two non-negative function r dot and say k dot, in addition we are assuming that they are non-negative continuous function on an open set, then we can, if we can write rt less than is equal to c plus the convolution running from, like, not convolution, actually it's not convolution obviously, tau r tau d tau for all t in an interval 0 comma capital T. Like in an interval we are assuming that we are having two functions, two are continuous, two are non-negative. Now instead of function of t, it can be also a function of x, that is your state variable, but they must be in the region of interest, they must be continuous and non-negative in nature. Then we can write, this is very important, that RT will be means always upper bounded by actually why we are doing all these things, that is because in case of nonlinear system it often becomes difficult for us to calculate the exact solution, and rather it is not desirable also. Not desirable in the sense that if it consumes a huge computational effort or if it taxes you severely, there is no point that you calculate the exact solution, and sometimes you may not be able to calculate the exact solution. You find the solution in form of a, like, sequence of solution may come. So there is different problems are there. I'm not going to in detail with that. Due to our time constraint, we have to means sum up it very quickly and yet comprehensively. So what at this moment I can say one thing, that is the solution, finding out a solution is not that easy, but what is our approach to circumvent that problem is to find out bound of that solution. So if I can specially means if we can find out, like, in space that our solution is confined within the region, or for certain value of function the function is upper and lower bounded. Here you can see that as I have mentioned, it is non-negative, so obviously it is lower bounded by that means zero value. But again, if you make sure that the function is upper bounded, then it will become very helpful for you. And then instead of finding out exact solution, if you can figure out that uh, it will be bounded, then from that you can claim that at least the function of interest which you are investigating is not uh, unstable or going beyond a range within your this frame of interest, right? So that is very important here. Now how to prove it? Let our s of t denote this is equal to c plus fine. For all we are considering this, so no need to write every time that which interval we are talking about. So it is implied from that first statement that RT is upper bounded by this ST, or T belongs to now. Further, if you obtain the differentiation with respect to independent variable, I am not going to use the word or utter the word time henceforth, because that may develop a means undesirable notion that it is always the time, or otherwise we cannot apply. But it is not the case. It is any continuous non-negative function we can apply this. So I will not use the time, rather I will use the term independent variable. So if we obtain the first order differentiation of s with respect to independent variable t, we will get this within a span of independent variable between a closed interval, this, right? Okay, sorry, just a minute. So now if we do a little bit of manipulation and side transposition, we can write s dot t minus kt rt is like, as we know that rt is less than s dot st, from this line we can write that this one is less than is equal to, as both the functions are non-negative, we can means conveniently interchange or means replace like rt by st without having any trouble. Now we can write s dot t minus right. So from that we can write exponential of tt this actually we are means this exponential of the function which we shown here, it is also means giving us more means will ensure that this will be less than the value. So now what will be observed that if you do this, what you will get is that in the next stage what we can write is like multiplied by the same thing. See, we can write it like this. Now see, the beauty of this whole thing is that the first let me tell you the pathetic thing that I have reached the end of this page, so I need to copy it in that next page. Got few portion left here. Now for this what you can see that this whole thing can be written like fine. So we can write it like s of t is upper bounded by c of exponential and which was what we are trying to prove, right? Because we have assumed that RT is upper bounded by ST. So if somebody is upper bounded by some function, obviously, like ST is an upper bound for RT and ST's upper bound is C exponential this. So obviously these hold good for RT also, right? So this is what Bellman-Grunwald inequality state, that the basic utility of this inequality is that it gives an implicit bound, right? You cannot know the or this even you do not need to know the explicit bound of the function, but you will get some idea, some intuition that okay, my system solution will lie or will be confined within this region. So that is the most important thing about this Bellman-Grunwald inequality, right? Now, if you want to obtain an explicit upper bound, then we can do it. That is also not a difficult thing. That if you notice the first equation from where we started, yeah, this one, here you can see that this explicit upper bound you can find out by putting this C is equal to 0, right? So that will ensure what, that RT identically equal to 0. Okay, so this is one means typical case. Now we'll go to our next lemma. However, means you must have noticed that before I go to that other one, comparison lemma, you must have noticed that one prerequisite of application of Bellman-Grunwald inequality is that both the functions must be continuous in nature. Negative, non-negative, that you can means break the function in segment to find out that within that domain the function may give you some non-negative nature or some exhibit some non-negative nature, or even if a function is totally negative in that region, you can just multiply it with -1 to get certain means like recast that problem so that you can apply Bellman-Grunwald inequality. However, there is one shortcoming of Bellman-Grunwald inequality is that it only applicable to continuous function. But what happens if the function is not continuous, means if it is not even like it is not even differentiable, then how to tackle that one? So what we'll do, we'll take help of a tool that is known as Dini derivative, and we'll try to means provide a solution using that Dini derivative. What Dini derivative states, like we can have four type of Dini derivative. Mostly we use that upper hand, we call it upper right hand Dini derivative. So that upper right hand Dini derivative is known as d plus. So this d plus vt is defined as limit, then it is to 0 plus supremum v of t plus h minus vt by h, where this limit like I wish I discussed Bolzano-Weierstrass theorem before this, but then there will be a bundle of theorem and you will not be able to get it. Anyway, so what we are trying to say, that limit supremum n tends to infinity is the limit, it is called the limit superior, the limit superior of a sequence of real number xn is a real number y satisfying what condition? Satisfying for every, or one condition for all epsilon greater than 0, there exists an integer n such that n greater than n implies xn is less than y plus this non-negative number epsilon. So this is one. The second one is that again we come to the end of that page. Just a minute. And the second point is very similar to the first one but quite different, that given epsilon greater than 0 and m an integer greater than 0, there exists an integer n such that n, where n is greater than m, such that xn is greater than y minus epsilon. So the pretty interesting statement. This is all what we have written there in a form in the last. While we are trying to define linear derivative, we wrote something like this. Like actually, we should write it here. Like limit superior. This. What does this limit superior means? It is like the limit superior of a sequence of real number. Why do we need a sequence? Because at that time when you are considering the function that is discontinuous, if you try to means apply this concept, then you can't get a single function. You will get a rather means a sequence you will get, right? A sequence of real number you will get. Different point will yield different values. And so now for all those sequence, what we are doing, we are defining a limit superior of a sequence of real number. Now how we are defining it? Like for a given sequence, we are having a real number y that satisfy any positive epsilon, where it is epsilon, there is no such bound that epsilon has to be integer. Epsilon is a real number that is greater than 0, fine, and an integer capital N such that the means what is a sequence? A sequence is a function that maps means your natural number to your any real number. For real sequence it is mapping. Why I am calling it mapping? Because you can see that you use one sequence, like you are having a sequence x. So how it would look like you are having 1.1, 1.12, 1.21, 1.3, 1.014, like this. So what is that issue here is that this sequence contains the position of this element is 1, 2, 3. So we can consider it like it is a function mapping of natural number to real number for real sequence. We can have it for like we can conceive a sequence that is that contains all the what to say that q. I just forgot what q is. It is denoted, that set is denoted by q, capital Q. I just forgot the name, unfortunately. So you can have something like f n to q. So Yeah, rational number. So integer to rational number we can have. So this kind of things we can do, and similarly for complex sequence we can also have a sequence where elements are complex number, but generally we consider real number, and means complex sequence is not at all common. Mainly, at least in our engineering field, we use a real sequence. Now, what we are trying to tell you that for means sequence you are having you are picking up natural number. Now, if you are means if you read this statement, it gives an indication that you have to pick up a larger value of n that is greater than a certain value of n. Like if capital N is 100, then you have to pick up any natural number that is greater than 100. So you may pick up 101, you may pick up 1000, you may pick up 10,000, but whatever you pick with index greater than 100, you will see that they will satisfy their value is less than a real number y plus and real number epsilon. However, that means there is a means also a problem associated with that. Like in this way, try to intuitively understand that you are actually imposing some upper bound for xn, but not any lower bound to xn. So what we are doing, we are again finding another means two numbers. Obviously m is an integer, so whenever your n, the index is greater than m, then you will see that xn is greater than xn is greater than y minus epsilon. So that is quite interesting. So one of these properties of limit superior is that if your, say we can say that like limit superior is that if number like zn less than is equal to xn for all the index, then we can say that, like what I am trying to say, if we have two sequences, one is zn, another one is xn, and if we see that limit superior of zn is always less than the sorry, not limit superior, means zn is less than xn for all n belongs to capital N, the set of natural number, then what we can infer regarding like what inference we can draw regarding this limit superior is that limit superior, your n tends to infinity, Zn is less than equal to limit superior n tends to infinity xn. So that is also a very interesting property. Now see that we can write from this property, you can write that if we have Vt plus h minus Vt by h is less than is equal to Gt comma h for all h in a half open interval 0 comma b. So you should be very clear that why we have taken the half open interval, because this limit h tends to 0, h is not exactly equal to 0, so this 0 is not included in your set. So that is why it is 0 comma b, means you can have any number that is very close to 0 but not exactly the 0. So basically here what you can have is that 0 plus, obviously, because you are considering the means right side of your 0, so you will be having then what you will get that now this is all about our upper right hand Dini derivative. We can have actually 4 different type of Dini derivative, but those are not required here. This upper right hand Dini derivative is sufficient for our purpose. We will not investigate about the other Dini derivative. So let us write the statement of comparison principle, that consider a scalar differential equation, that is u dot f of t comma u, ut naught is equal to u naught, where f of t comma u is continuous in t and locally elliptic in u. So it is continuous in t for all the values of investigation, and locally elliptic in u for all t greater than is equal to 0, and for all small u belongs to z, small u belongs to j, not to z, belongs to r, right? Means j is a subset of r. Supposedly proper subset of r. Now, like we can write like further, let t naught comma t, where this t could be unboundedly large, means it can be infinity also. So be the this interval be the maximal interval of existence of solution of your ut and suppose ut belongs to j for all t belongs to that interval t0 comma t, sorry, t0 comma t. Yeah, as we have considered it can be unboundedly large, we cannot use a closed interval, we should make it open. Yeah. Now, so basically we are trying to ensure that ut is a ellipsis, that is why we are writing so many things. As mathematicians are laconic, they do not want to speak much, they rather they rely or they behave like means those people of ancient civilization who depends on different types of symbolic representation. So now this line is very important. Let Vt be a continuous function whose upper right hand derivative d plus vt satisfies the differential inequality what is the differential inequality? That is d plus vt is less than is equal to f of t comma vt, where your vt naught is less than u naught, with your vt also belongs to j for all t belongs to that half open interval t0 comma t, then your vt is lower bounded by vt less than is equal to ut for all t belongs to t0 comma t. So let us, before we do anything, try to understand what do you think that means evaluation of upper right hand derivative. I think as none of us are mathematician, let us rely on example and try to calculate that how we can figure out upper right hand derivative of a function. I will show you just a minute. Well, so here we go. Let me take you an example. I'm not sure how much this example would help you in understanding that concept of Dini derivative. But I hope it will help you to a certain extent. It is the value of x. The first one you will get if x belongs to our set of rational number. Actually, we should write a stylish O Q, but yeah. And if x doesn't belong to that stylish Q, then it is 2x. So what is required that we need to calculate if I want to calculate d plus f0, d minus f0, d plus f0, d minus f0. Actually, if we go back, you will see that in our derivation, sorry, not derivation, rather, we are happy with d plus of some value. So where actually h approaches 0 from the upper side, but here our target is not only to this much is sufficient, means if you can understand the meaning of this, that is sufficient to understand that comparison means, the idea of comparison lemma. But what is my goal is to give you a slightly different calculation, so that will make sure that your understanding of the previous calculation which is needed and the calculation which is not needed, the calculation which is not needed for the means this particular purpose, will also enhance the understanding of your idea on that other means what is needed. So with that, let me move to my topic and calculate without wasting time. So what, again, I have reached the end of this page, so I have no other choice than copying it. It has become a problem with me for last all my lectures. Like whenever I try to conclude something very interesting, I realize that I have reached end of the page. So that is very bad. Anyway, we cannot probably destined to face this kind of difficult situation. So now let us do it. So how you are supposed to define this person? This one is like limit you are approaching from upper side, so h to 0 plus now here like that. First we need to find out the concept of limit superior. So limit h tends to 0 plus superior, here we are considering 0 k this so how that superior will be, like whenever see, although we are having two part like x and 2x, x for the rational means supply and sorry x for the rational part and 2x for the irrational part. But obviously when you are approaching to 0, you cannot like jump from one rational to another rational and skipping the irrational part. So obviously when you are taking that kind of sequence, it will always be 2h in nature. So you will get something like h tends to 0 plus is 2h by h. So naturally what you get, limit h tends to 0 plus, or this is basically your d plus f0 is equal to 2. Now like if you approach from the left, then what you will have, if you approach from the left, you will have something like d minus f0. Now here one thing I would like to make it very clear before we go and calculate it. Let us define the function once again. The original definition of function was like mod x mod 2x, where this x belongs to q, stylish q of course, and when x does not belongs to this stylish q. Now here when you are talking about f of x when it is less than is equal to 0, then it will be perfectly okay to write it in this way, because for that if you pick a value of x that is already a negative number, it will return you a negative number. This one is valid only in this region, means the left side of your x is equal to 0 point, you are taking the values, right? Now see what we can do here. One again we have reached the end of this page. That is the constant trouble I've been facing, probably due to my selection of font size that is too big. Anyway, so here one thing is very clear to us, that if we consider a region where x is less than 0, then minus 2x, try to understand this, minus 2x is greater than minus x. So when we again try to define the same concept of limit superior, like limit h tends to 0 minus, means you are approaching from the left side, f of 0 plus h minus f of 0 by h, then what you will get is that limit h tends to 0 minus, then here it is like supremum of 0, sorry, hk0, obvious, because 0 is the biggest possible, means what you can say that index element you can have here. Now so if that is the case, then what you will get finally, that will result in limit h tends to 0 minus is like minus 2h by h. So you will get minus 2. So d dash gives us is equal to, in this case is d plus f of naught is equal to d minus f of naught. You are getting certain idea. In similar way you can calculate the other part, that will be just you have to take or replace the supremum by infimum, and I can show you, like if I have to calculate d plus f naught, this is actually that taking or talking about infimum. So here limit h tends to 0 plus, but instead of supremum here it will be an infimum. Now here it is f of 0 plus h minus f of h by h. Here you can see that it is a very obvious thing that when you consider the value between 2x and x, obviously it will result you x, so it is h, not 2h, so this will result 1. And I hope now you have got some idea. You can calculate this also. This will result sorry. So this will basically become minus h by h, that is minus 1. Fine. So this is very interesting things here. Now with this knowledge of these 4 Dini derivatives, while only the first one is needed, let us revisit once again the claim of comparison lemma. Here what I wrote is that a function u dot is equal to f of t comma u, where we know the position of initial or starting point ut naught. A function f t comma u is continuous in t and locally Lipschitz in u. So for all t greater than is equal to 0 and for all u belongs to j, where j is a proper subset of R, quite possibly that j is not equal to R, but j is the subset of R, in which your this claim for satisfying locally Lipschitz with respect to u get validated, and then you can have semi-closed interval or a half open interval like t0 comma capital T, where this there is no such restriction posed on capital T. T can be unboundedly large, so T can be infinite. So with the maximum interval of existence of solution of ut, like obviously you can have, as we have discussed already, that solution may also, we can have different solution. We are actually trying to like pick up a chunk of time, or means whatever you understand by t. It is, we are trying to pick up a chunk of that with respect to which we have continuous variation of our function, and the solution is existent in that particular chunk of our interval. So in that case, what we are getting, that if we find, then let Vt be a continuous function whose upper right hand derivative is satisfying this differential inequality, then we can say that this one Vt naught is equal to this. Now we will see a proof of this comparison lemma. Yeah, one thing we can do, that instead of proving this complicated comparison lemma like a mathematician, what will be useful, what I suggest, that let us study a few equations. If any one of you are interested in that kind of mathematical rigor, in my understanding at least a few of you should, if you want to pursue your further career in theoretical analysis of control system. So you can communicate with me. I would love to show and discuss such proofs with you, but for all 23 students, it may become something will be like means a person who is suffering with upset stomach. It will be like suffering means a very rich Hyderabadi biryani or something, or very means rich dish to a person who is suffering with upset stomachs. So that may cause or means a very heavy continental dish to a person who is suffering with upset stomach may result undesirable situation. So better as an individual, as a student, you judge yourself whether your stomach is ready to digest extra, whether you can means take or consume those delicious and means heavy dishes, or you will be like be happy with only the staple food, daily staple. So that you need to decide. So this has a unique solution for some t greater than 0, because you can verify that fx is locally Lipschitz. Isn't so? Fx is locally Lipschitz. Like if you take any certain range of x, any finite range, then you will find that it is locally Lipschitz. Now we take another function. Let v of t is equal to x square t now obviously v of t is differentiable, and if you obtain the differentiation of v dot t, you will get something like 2 xt x dot t, that further yields minus 2 x square t minus 2 to the power like x4 t. Fine. So this is clearly less than minus 2 x square t. Now means obviously we are considering positive time, and this is always true. Now here what we can say that Vt satisfies the differential inequality that v dot t is less than is equal to minus 2 Vt, right? And here we can say v0 is equal to what? v0 will be, if your x naught is equal to a, the v0 will be a square, right? Now let ut be a solution of that differential equation. Then what you will get? U dot is equal to minus 2u. Just means considering this u dot is equal to minus 2u, and u naught is equal to your square. So these two yields, u will be how much? U will be a square e to the power minus 2t. So if that is the case, what we can write that by comparison lemma, that mod xt is equal to under root vt is equal to, means less than is equal to e minus t into a. So basically this gives this bound on e to the power minus t a, means whatever be the case, then it will be constant even if you consider variation of xt. Xt is like if you consider, obviously xt should be monotonically decreasing, like some, it will be like upper and lower bounded by your plus a and minus a, right? Whatever be the value you get, it may so happen that it means decays monotonically. It can have certain oscillation, but what we can say that it will never leave this band of means at t is equal to 0, it is minus a and plus a, and this envelope is governed by e to the power minus t. In both the side it is e to the power minus t. Now let us take another example. Let us consider that x dot is equal to f of t comma x, that is minus 1 plus x square x plus e to the power t. For that you have x0 is equal to a, and this also we can expect that has a unique solution over the interval 0 comma t, where t greater than 0, any value t greater than 0, because here f t comma x, the way we have defined it, it's locally elliptic over x. So if that is x, then we are actually investigating or interested in finding an upper bound for this. Obviously whatever we will get as an upper bound for this one, if we negative it, then we will get the lower bound for that, means negative part of that solution. So what we can do is that, like the previous case, we can start with that same thing. V of t is equal to minus v of t is equal to x square t. Like we are keeping everything same, just we have introduced another additional exponential time here. So what you will get here, you will get v dot t will be, instead of writing the intermediate steps, I am writing the final one, minus 2 x square t minus 2 x4 t plus 2 xt et. So we can write it totally in terms of v, like it is minus 2 vt plus 2 root under vt into e to the power t. We are taking only the means positive one, so that is why we just wrote it in this way. Now what we can have is that we can apply comparison lemma with this differential inequality, but here the difference with the previous problem is that now the resulting differential equation is not easy to solve. So what we can do is that instead of means considering this exact one, we can have a different choice of Vt. That is, we start with Vt is equal to mod of xt. So if we means just change our mod of xt for all value of t not is equal to 0, what you will get? Vt is differentiable and it's given by v dot t is equal to your d dt. Just a minute, let me check. Yeah, it's recording. D dt root under x square t. So this gives us, it will be like minus mod xt 1 plus x square t. As it is squared, so no need of mentioning mod, plus xt by mod xt e to the power minus t. Sorry, e to the power t. E to the power t. Now, it is interesting to note that this 1 plus x square always result greater than 0, right? Or we can say greater than 1 also. So we can write it like minus xt and the other part, like we can write the whole thing like v dot t is equal to less than is equal to minus vt plus et, because the second part can result in plus 1 or minus 1. So whenever you are taking the less than is equal to, you are giving yourself the liberty of taking the highest value, because obviously the left side is going to be very small. Now what we need to do, that at xt is equal to 0, we need to evaluate the one like so. Basically you will get, when your xt is equal to 0, at that point, at that discontinuity point, what you will get here is that x of t plus h norm by h. So this x of t plus h, this can further be written like when we have reached the end of the page. So now here one thing is clear, that this is equal to what we can write, that norm of x of t plus h by your h is equal to 1h t to t plus h So this will result in what? This will result in, because we know that this is x dot. If you are not able to get this step, you can follow it from here only. then what we will need to do here, that we can write it is equal to f of t comma 0 plus, we can take this 1 by h inside, and we will see that f of t comma 0 will come up with 1h multiplied with it. So numerator and denominator h will cancel out each other. So you will have here sorry. That is very obvious thing is less than, we will apply the property of non here. Means it is not non, but one way you can say it is norm 1. So that will be right. This will be the case. Now here, as this is a continuous function of t, we can apply the notion of eta delta continuity is epsilon delta. So for any epsilon greater than 0, you can expect there exist delta greater than 0, such that for all tau minus t less than delta, we can say that f of tau comma x tau minus f of t comma xt less than epsilon, because we have assumed it is continuous in nature. So for all h is vanishingly small number, so h less than delta, we can show that like this whole thing, this second part, this one is less than epsilon. Agreed? So what we can see that if we allow that limit superior, limit h tends to 0 plus, we'll get 1 by h t plus h f of tau comma x tau minus f of t comma xt d tau. Is equal to 0. So thus your means, if you take that d plus vt, d plus vt will be how much? D plus vt will be that one part we have proved it is 0. The other part will be how much? The other part will be that will be right. So this is true whenever xt is equal to 0. So if that is the case, then for all t belongs to 0 comma capital T in this range, we can have d plus vt less than is equal to minus vt plus et. By definition, your vt is non-negative and v0 is equal to mod a. So if you consider u be a solution of that equation, then u dot is equal to minus u plus epsilon t, and if you solve it using comparison lemma, what you will get, like not solve, that if you apply comparison lemma, you will get your vt is less than is equal to ut is equal to e to the power minus t well, this is true for all. Right. Now here, if you want to find out the upper bound of t, then vt is obviously finite as long as you are considering t is finite. Vt is finite as long as t is finite, and then it will satisfy this is the bound by which your equation is bounded. So a long problem, I wish, and not only wish, if I fail to show you the many other solution of numerical by 11, what I will do, I will compare, not compare, rather cover the syllabus by 11, and after 11 I will upload optional video on your extra problem solving that you are supposed to do by your own effort, but I'm quite sure my experience says that only a few will do, or rather nobody will do. So I'll upload a video on that different solution of different problems, because in my understanding, what I told to my BTech student, what I told you, that as much as you solve problem, you will learn, but without solving problem, nobody learns.